So thank you to let me the possibility to speak today. Oh, maybe it's not on here, or it's on the microphone. You read me well? You may have to okay. Now talking. Okay. Oh. Okay, it's okay now? Okay, so I'm Daverio. I'm a PhD student of Martin Kunz. And this work is done in collaboration with Martin Mark from Sussex University, John with Gila from Geneva University, and Neil Davids just quit the academics, so he's now in Freedom Company. Okay, so I will speak about our simulation. So first I will speak a bit about the topological defects. So cosmic string are topological defects. So to understand what is a cosmic string, you really have to understand what is a topological defect. Then we will speak a bit about the cosmic string we are simulating. So it's what we call the Abelian Higgs model. Then I will give a general description of the simulation, give a bit of the simulation output as we are in production now. We will have our first result in something like 3 months, so I cannot give you some results really. Then I will show you some benchmarks in simulation, and then I will speak about Latitude 2D, the framework which we developed to do this simulation. So, what is a topological defect? A topological defect is something that happens in the field when you have two elements. The first thing is you have to have a topologically non-trivial vacuum. Okay, so first term, the vacuum. The vacuum, I'm sure you all know what it is the lower energy state. And what is a topologically non-trivial topological space? It's simple. It's not so easy to understand, but for example, R is a topologically trivial because you can take R and shrink it to a point. But now, if you take two intervals in R, you will never be able to shrink them in a point. You will be able to shrink them to 2 points, and then it's what we call it's not topologically trivial. Two separated areas are not topologically trivial. So that's it. So then you can imagine a circle, for example, is not topologically trivial. You cannot shrink a circle to a point. If you shrink it, you will still have a circle. And the second thing is a damping term that makes the field fall in its vacuum. Okay. So the simplest example that we can imagine is the Higgs field. Let's take a scalar Higgs field, a real scalar Higgs field. So we have this kinetic term and the potential term. And the potential is, as I draw it here, so we have two voids, two separated voids. So we are in the case we have two separate places, so it's not topologically trivial. Then we put that thing on a FRW metric. So it's the metric where we have an expansion of the volume. So it's that metric. And when we compute the equation of motion, we find that. And we have this term, which is a damping term, which generated the field to fall in this vacuum. So here we have the non-trivial topological vacuum, and here we have the damping term that makes it fall in this vacuum. So now we have all the elements. So now what is a topological defect? So you have a field in a one-dimensional field. So if you have only one component, and in a one-dimensional space, 2 is the visualization. So you start with the field really excited, so he can be anywhere in its value. He can just travel here anywhere. And then when you add the damping term, falling in this void, he will fall in that void or in that void. You really can imagine the experience with a little ball that you put in a recipient that has this form. And it's it will be very, very hard to know in which hole the ball will fall down, because it's really depending on at which moment, at which speed the ball will arrive at the top here with a zero velocity. So it's really difficult to know in which vacuum it will fall down. So, but basically the field will fall in this vacuum. So let's imagine that in that area it falls in the lower vacuum, and in that area it falls in the upper vacuum. Then the field is continuous. So it for sure will need to pass to the zero. And in the zero, what we have the maximum of the potential here. Yep. That was the problem. Okay. Sorry. Okay, so it will pass to the zero, to the maximum of the potential, and therefore the energy here will be bigger than here because of the potential contribution, and also because of the gradient contribution, but because here the field is basically flat, so there is no gradient, and here too, and here no, there is a gradient, so therefore you will have the energy will be bumped where you have these things. And this bump of energy is what we call the topological defect. Now, why it is conserved? It's really just because of the continuity of the field. If you want to take that point and let it move to here, you have no choice to pass to the maximum of the potential. So therefore, what will happen if these things go down? It will only move the topological defect to another area. And therefore, the topological defect is conserved. The only way to destroy a topological defect is to sum two how you say that? Shit, I don't know in English. Okay, is to have something that is like that, and then you have two topological defects that goes and have shock, and then it can annihilate the topological defect. But it's the only way. Okay, so now we can move on what we are simulating as. It's basically exactly the same thing. The only difference is now we have not a real scalar field, but a complex scalar field. So we have two components of scalar field. And we put it in FRW metric, but we had electrodynamics. That's why we call Abelian Higgs model, because we have an Abelian symmetry, a U1 local symmetry here. You also can call them local cosmic strings because you have a local symmetry. Evidently, you can imagine dozens of Lagrangian that will create exactly the same effect. You can have superconducting cosmic string. You can have global cosmic string if you put out the U1 gauge. And you can imagine with the SU2 gauge, a non-Abelian Higgs model or something like that. That's it. So now let's move to the simulation. The simulation is the simulation general description. So the idea of our work was to move to 4096 cube structured and static mesh. The previous simulation was at 1000 cube point. And so we multiply, as we are using exactly the same space resolution, we multiply the volume by a factor of 64. And the basic idea is we make evolve the film with a staggered leapfrog, and we have two outputs, what we call the UETC, so it's the energy momentum unequal time correlator. This is what we use to make CMB CMB prediction, or yeah, the CMB constraint due to the cosmic strings. And the second output is what we call the windings. It's basically the zero point of the field, and as we see in this picture, the zero of the field here is the topological defect. So we only save the position of the topological defect, and we did it because before we were saving the energy density, which give exactly the same information, a bit more, but not so much. The only things that we can see more with the energy density is the scalar radiation that we cannot see here. And, but here the windings is 10 gigabytes. It's not really stable because the number of string is not fixed, so it can be between 10 and 50 gigabytes max. No, yeah, maybe, yeah. And we save that to be able to study the loop statistics and also the string velocity. Okay, some number about the simulation. So we have 40 float per site of the lattice. So it means 11 terabyte in memory in the RAM. We make evolve the simulation up to the time that the light have traveled to the half of the box, because we are simulating in a periodic boundary condition, and we don't want to see the periodicity affecting the things, because we are simulating the universe, and the universe is for sure not periodic. So it means around 10,000 time step. And we need to perform the FFT of the energy momentum tensor to be able to have the UETC, the analytical time correlator. So we need to perform FFT of 2.75 terabyte of memory, and we perform it 150 times per run. And one run is 14 hours on Monte Rosa on 34,000 core, yeah, nearly 35,000 core. So let's see a bit of, I'm a bit fast. Let's see a bit of the output. First things, the windings. Here we can see the difference that we have between our run on previous simulation. The fact that we have multiplied the box by a factor 64 means also that we have multiplied the number of strings by a factor of 64. Because the total length of topological defect is in fact really linearly related to the volume of the simulation. And that's exactly why in the beginning, as we are simulating an expanding universe, we have a small volume, therefore a lot of string. And at the end, we have a really large volume. The simulation means a really large volume, and then we have much more less string. And these two snapshots are done with exactly the same initial conditions, so it's white noise. It's basically white noise. So it's not exactly the same initial condition. It's white noise generated randomly, for sure, for 4,000 points or for 1,000 points. And it's exactly the same time step. So you really can see here the improvements of the data. And the really good things that we see is here in blue we have a loop, and here we have only one. And here all the blue things are loop. The code that triggers the loop is not really working very well, and I should fix it a bit more. I accept to have at least twice the loop, because there is some events, maybe like this one, which is a loop, but not trig. So the idea of the analyzing of this data is to first make a map of every string, meaning that we detect we trig each string, we save in a file all the evolution of each string, then we can build up the velocity and everything like that. And we can really follow one string by one. So I hope that in 3 months I will be able to show one picture like that, and to press one button, wait 3 seconds, and have only one string, and have the evolution of this string on only one string. And that's not so easier, because there is string collision, and a string collision, maybe I draw it, it will be the easier. If you have a string like that, and the second one like that are moving together, and then there is a collision. Here we have the collision, and you have this strange event where you have a point which have 4 strings that goes from that point, and that is not a topological defect. It's not stable. So this point will for sure disappear. And in fact, what happened is the part with the higher curvature which will survive, and therefore you will have 2 strings like that. So you have strings that merge, strings that cross on separated, And also, if you have only one string that does something like that, and you have a collision that appears here, you can generate a loop. So therefore, the number of loops are not stable because there is loop formation. And it can be, it's the most difficult thing that we have to do now is to find a way to create a really good mapping of all these events. The second output that we have is what we call the UETC. And also here we have a plot of the whole simulation UETC here on the new UETC that we build. And as you see, we are able to reach larger T, because here it's T over, okay, the UETC, we correlate it with reference time. So here it's the time of the simulation divided by the reference time. And here it's K from K, the pre-index, multiplied by T. And this is the correlator for the scalar part of the UETC, because we have 10 components, so there is scalar part, vector part, and things like that. And so we see that there is a really large improvement here. And the really interesting things for us is to have this part here with much more, with data. Here, in the past, what they was doing, it was to interpolate what is the data for here. And in fact, the main contribution for the CMB is for sure the bump. But this part here is also really important because the bump is a really clear signal, but we saw that for the CMB, this clear signal can contribute at maximum to 2 or 3%. But then this part is at the end of the power spectrum, is more at the end of the power spectrum, and there is a much more bigger contribution. So it's better to have data here than to have the bump. Even if we do not have the bump, we cannot say nothing for sure. That's it. Okay, so let's speak about the simulation benchmark. So here I show the efficiency of the different part of the simulation. So the UETC build efficiency and the evolve efficiency. I do not have really benchmark for the winding things because I only tested for the 4,000 cube lattices, and I only have 1 point or 2 points, so I cannot say it's really a benchmark. So we see that the evolve efficiency is not so bad. For a 2056 lattice, we are able to use up to 2056 core with 85% efficiency. No, that's not completely true because I start at 4, so I think it's more like 82 or something like that. And if we look at higher lattices, the efficiency is still, I think, okay. And for the UETC, okay, why we see sometimes more than an efficiency bigger than 1 is just because the algorithm is really optimized to large number of core and large lattices. And in fact, sometimes this bump is really due to data locality. So in the FFT, we have a massive all-to-all, massive transposition of the lattice. And the local transposition algorithm that I use is much more better in that area than in that area. And that's why we see this bump. And the last thing is the I/O bandwidth. So this is not the bandwidth of the winding writing. This is the bandwidth of the field writing using HDA5 data format. It was the first thing that we were thinking to save. So we were thinking to save about 2.75 terabyte snapshot and to have something like 50 snapshots. But then when we test it on Monte Rosa, it appears that it's clearly not feasible because if we reach 5 gigabytes, we even reach nearly 8 gigabytes per second when the scratch was YSORM, but it was really when there was no user of that scratch. But then that's the ideal case, because that's when the I/O is not used by you. And when you use the I/O, the bandwidth just go down and fall down, and we reach something like 100 megabyte per second, something like that. But I'm sure that it's some moment where the total I/O of Monte Rosa is around 8 or 10 gigabytes per second, and we are sharing the bandwidth. That's only that. So due to that, the speed of writing can move from 20 minutes to 4 hours, let's say. So we completely stopped to use these things because it's not really useful. But then it's in the code and it works pretty well. So basically, to perform this simulation, we developed a framework, a C++ framework named Latfield 2D. The first version was developed by Martin Marsh and Niels Bevis. It is a pure MPI code. The first version was a one-dimensional processor grid with serial I/O and without an optimized FFT algorithm. And what I have written is the second version. What I have done is to move from a one-dimensional processor grid to a two-dimensional processor grid, add parallel I/O, optimize the FFT algorithm for 3D qubit lattices, and add an external I/O server. So let's speak a bit about the I/O because I think it's a bit interesting. We are using parallel I/O using HDF5 parallel. The library does everything, so you really don't have to care about anything. It automatically recognizes data type. It automatically recognizes file type, meaning scalar, field, vector, tensor, or things like that. And it will arrange the HDF5 data set well to be able to read it in visit with Pixie, thanks to Jean Favre, who have modified Pixie to be able to use it with parallel visualization. And you do it just by one call, save HDF5 file name. So it's really easy to use. And then I also, to be able to write these winding things really fastly, I had an external I/O server. So it's basically a number of nodes that are used just for I/O. And it's not, that's what I want to speak a bit about that because it's not really as we have the habit to use I/O. So it's non-blocking I/O. You don't choose if you write a file or not. The data transfer, but the good thing is that we have seen on Monte Rosa with 2,000 I/O cores, bandwidth up to 1 terabyte per second. And we are writing 10 to 20 gigabytes. So now the winding writing is completely neglectable, and we can try to write as much snapshot as we want. And that was the purpose. I developed these things to be able to save as many snapshots as possible. And with this idea, it's a bit weird, I know, because usually you run a simulation and you want the output. You don't want to say, OK, maybe I will have it, maybe not. But as we are really interested mainly by the UETC, this is additional science that we can perform on the simulation. We don't want to slow down too much the simulation, because one run is around 500,000 CPU hours, so we don't want to overload the execution time. So we want to save as much as possible, but without taking any time from the simulation. So how it works, basically, you have two bunch of cores. So it's also a pure MPI part of the code. You have two line of communication. Line for the data transfer, which is MPI send rec, because it's the faster way to transfer data. And it's used to transfer the data. And there is synchronization line, which use one-sided communication. But who transfer just flag, not data. So basically, the I/O, the external I/O works like that. The compute core send the flag to the I/O that he wants to open the file. The I/O cores answer, do I am ready to take data or do I am not? it can be not ready if it's a moment where the I/O course is writing on the disk the data. So if it's ready, it sends a flag to the compute node. OK, you can send me some data. Then the compute course sends data to the I/O. And the things is, how you say that? You send small amount of data, and what I did, I do some computational, some send, and then computation, send in switch, and it's the fastest way. Because if you want to send a too big amount of data by once, it's not really good, I think. And then when all the data is sent, the compute node sets a flag that it's OK. You can write the file and continue the computation. Evidently, so it works like that, but evidently you can put a flag here or something like a while loop that just waits, re-ask to open a file up to the time that the I/O is ready. So it's really up to the user to be sure to save or not sure to save. But this was, for us, it's the best, because as we have more data in the beginning of the simulation than in the end of the simulation, because we have more string at the beginning than at the end. And also, as we are saving the UETC more often in the beginning, because we are following a log scale, so we save more UETC in the beginning. So in the beginning, we are writing more, but we have more computation. So it's really stable, and it's balanced by himself to find how many snapshots I am able to save. So basically, what I ask to the code is write every time step, write the things. And it will finish by writing every 5 time step or every 10 time step with a stable way. And that's the really good things, I think. OK, and then I can switch to the conclusion. So in 2012, we are running in production. I think that I've discussed with my boss this morning. I should have changed this to date. It will be March 2013, the loop statistic output, and maybe June 2013, the CMB contribution, because we are waiting to the Planck data to do this loop contribution. And what we are thinking for future investigation is running with smaller growth factor. I didn't speak about that, the growth factor in our code. So basically, if we are simulating an Abelian Higgs strings will shrink really, really fast. And what will happen is, after, I don't know, maybe 10 time step, you will have one string which will be much, much, much more smaller than your resolution. And therefore, then you are not enabled to really do simulation on that, because you lose string. String will shrink and be lost between 2 points of the lattice. So therefore, we have to make them grow. So at each time step, it shrinks and we regrow it. And that's not really physical. But we know that with 4,000 cube points, if we have a smaller resolution, so for example, if we simulate a physical volume 1,000 smaller than ours, we will have 10 times more resolution in all dimensions. And then it could be possible to turn off this growth factor. And this is one of the biggest criticisms that we have of our simulation, this growth factor, which could be not physical. But we have already tested on really smaller simulation, and it really looked to have no influence. The second thing is we would be very happy to be able to study loops with very high resolution. So for example, only one loop in 4,000 cube lattices. Because right now, there is 2 ways to simulate cosmic strings. What we do is field simulation, and the other way is to perform Nabu-Goto simulation. So really simulated the string themselves. But then you have to add a lot of ad hoc things to make the evolution correct as if it was topological defect. And what we saw is that loops are unstable. What they saw is that loops are stable. And they just say that you see loops are unstable because you don't have enough resolution. Your loops shrink, and then you have one loop. It's around that, I think. You have one loop on something like around 7 points. The loop is around 2 points. The string is around 2 points. So you can imagine that your void here is around 3 points. And that's really not a lot. And maybe it's just numerical effect that the loop disappears. We don't think so because I will not enter in detail. From theory, we don't think it's a numerical problem. But people who are doing Nabu-Goto simulation say, okay, this is just a problem of your simulation. So then, if we are able to have a really large loop and to see them disappear when the loop is at something like 500 points of resolution, then no one will be able to say that is a problem of resolution. So this will be, I think, one of the next year's study. And also there is another thing that we really want to do is to make the loop supraconducting. Oh, this is a French-English word, I think. And the good things with superconducting loops is that as it's supraconducting, you have a lot of current in, and the current make the loop stable. So with superconducting loop strings, you will see a lot of loop of a given radius stay in the simulation. So it could be interesting to simulate them. And it could be really interesting to study loop collision. Like that, we will have two loops that are stable, and we can make them collide. And we can try to study if there is topological invariance within the collision. And if we find some, it could be related to conserved things within a collision. And then we could do some particle physics. Not the model standard, but for sure. But we could do something that is close to the particle physics, meaning that you have a list of particles with a number of invariant things, and you make collision, and you create new particles with it. And I think this would be really, really interesting. And this will lead us to the way to the superstring theory or something like that. But evidently, we will never be able to do the standard model, because we know from superstring theory that we need more than 4 dimensions to do that, and we will never be able to have a 4,000 cube lattice in 11 dimensions. That's for sure, I think. Maybe not in my life. Okay, and I think I have done with that. So if you have any question, just feel free to ask.